Inversion is applicable to lines of pitches in tonal music. As shown in Figure 1, when inversion is applied to a line of pitches, the contour is preserved, but is turned upside down. For example, the ascending minor third followed by a descending perfect fourth at the beginning of the original melody becomes a descending minor third followed by an ascending perfect fourth in the inverted version. Note that the order of the pitches is also preserved after inversion. In posttonal music, inversion is applicable to both lines and sets of pitch classes. Since the concepts of pitch classes and sets are employed, contour and order are not necessarily preserved. This is illustrated in the following examples. Inversion involves two operations: mirror inversion and transposition. It is designated as TNI. Tn means to transpose the pitch class by n semitones. I means to invert the pitch class around 0. In other words, the axis C. It is important to note that inversion is always performed before transposition. First of all, let's take n equals 0. The inversion is expressed as T0I. According to the definition stated in the previous slide, we will invert the pitch class around 0 first, followed by a transposition of 0 semitone. We pick the pitch class F as our first example. It is 5 semitones above 0. Therefore, after inverting around 0, it becomes 5 semitones below 0. In other words, the pitch class G. N equals 0 represents a transposition of 0 semitone. As a result, inversion of pitch class F through T0I gives the pitch class G and can be denoted as T0I5 equals 7. We use pitch class B as another example. It is 11 semitones above 0. Therefore, after inverting around 0, it becomes 11 semitones below 0. In other words, pitch class C sharp. Since n equals 0 implies no transpositions is needed, C sharp is already the final result. The inversion of pitch class B through T0I gives the pitch class C sharp and can be denoted as T0I11 equals 1. Let's change to take n equals 7. The inversion is expressed as T7I. That means that we invert the pitch class around 0 first, followed by a transposition of 7 semitones. We use pitch class A as our first example. It is 9 semitones above 0. Therefore, after inverting around 0, it becomes 9 semitones below 0. In other words, the pitch class E flat. This time, n equals 7, which means that the pitch class E flat needs to be transposed up 7 semitones, and therefore B flat is the final result. In other words, the inversion of pitch class A through T7I gives the pitch class B flat and is denoted as T7I9 equals 10. One more example is given here with the pitch class G sharp. It is 8 semitones above 0. Therefore, after inverting it around 0, it becomes 8 semitones below 0. In other words, the pitch class E. N equals 7 means that the pitch class E needs to be transposed up 7 semitones, and therefore B is the final result. Therefore, the inversion of pitch class G sharp through T7I gives the pitch class B and is denoted as T7I8 equals 11. It is noteworthy that T and I is its own inversion. In other words, any pitch class that is inverted by some T and I operation can be reversed back to its origin by performing the same T and I once again. We will illustrate this with an example. In the previous slide, we have shown that the inversion of pitch class A through T7I results in the pitch class B flat. Now we perform the same inversion, T7I to the pitch class B flat. Since B flat is 10 semitone above 0, after inverting around 0, it becomes 10 semitone below 0, in other words, pitch class D. N equals 7 means to transpose it up 7 semitone, resulting in A as its final destination. Consider the two inversions in this example. Inverting the pitch class A through T7I gives B flat, while performing the same operation on B flat, we reverse it back to A, the original pitch class. As mentioned before, inversion can be applied to a line of pitch classes. We will use Schoenberg's string quartet number 4 first movement measure 1 to 9 for illustration. In this slide, the upper line shows bar 1 to 6 of the first violin part, while the lower line shows bar 6 to 9 of the second violin part. Each pitch class is denoted by the corresponding pitch class integer. Careful examination reveals that each pitch class in the lower line is related to a corresponding pitch class in the upper line by a relationship of T9I. The blue dotted lines indicate the pairing of related pitch classes. We may use the first two pairs of pitch classes to verify this. The first pitch class in the upper line is 2. To perform inversion T9I, we first invert it around 0, resulting in the pitch class 10, in other words B flat. Then we transpose it up 9 semitones, reaching the pitch class 7, in other words G. The second pitch class in the upper line is 1. To apply inversion on the pitch class, we first invert it around 0, giving us the pitch class 11, in other words B. Then it is transposed up 9 semitones, resulting in the pitch class 8, in other words A flat. If we go through each pair of pitch classes connected by the blue dotted lines, we will notice that the two lines of pitch classes are related by inversion T9I. It is noteworthy that the contour of the upper line is not preserved in the lower line after inversion. See the red and blue contour lines respectively. Although the contour may not be preserved when inverting a line of pitch classes, in the present example, the ordered pitch class intervals are preserved through reversed indirection. Let us recall the pitch class integers from the previous example to illustrate this point. The ordered pitch class intervals between adjacent pitch classes are highlighted in blue. The relationship between the two series of ordered pitch class intervals may not be obvious at first glance. In fact, they comprise ordered pitch class intervals that are reversed in direction.